Question?
Yeah, I think this relates to what you just said, but so taking the first one that was written, not the one you just put on,
Yeah.
but taking that sort of the default, the one with the OCH3, that's faster, the one with the nitrogen, that's slower.
Yeah.
But you can also ask us about, and I saw this on the worksheet, if the molecule's a bit bigger, you could put the alkene in a different spot, right?
Sure. Yeah.
If it's more or
And
less.
so then,
Yeah.
and that's what I say about the alkyl groups. All right, so let's do. All right, so if those react with HCl, if the four alkenes I just drew are the things that react. Now there's not a strong electron donor on them. There's not a strong electron withdrawing group on them. But there's a different number of alkyl groups. So I've drawn them in order, right? Here we've got 4 donors. Here's 3, here's 2, here's 1. So in this reaction, right, in this reaction where the alkene's giving electrons away, the alkene's going to be a base. The alkene that's got 4 substituents is going to react faster than the one that's got 3. Will react faster than the one that's got 2. And this is a little weird, because if I ask you guys to rank these in stability, how stable is the double bond? This one is the most stable, the one on the end is the least. And that's counter to reactivity in electrophilic addition. Saw some heads jerk up on that one. I think I actually was about to land my message and then I confused it. So typically we would say the more stable something is, the less reactive it is. And that is generally true. But it depends on the type of, stability is always relative and it always depends on the conditions. There are plenty of molecules that are super stable once they're wet. Well, so then they're not that stable because we live on a very wet planet. You can't just set them out on the table, they'll decompose. But if you put them in a vacuum or somewhere that there's absolutely no water, they're great. So generally speaking, in terms of stability, like if we were going to burn these, the most stable one is the tetrasubstituted alkene. But it also winds up being the most nucleophilic. And so if you expose it to an electrophile, HCl, really any of the reactions in chapter 8 except for H2. The tetrasubstituted alkene there will react faster. Right? The addition of hydrogen to an alkene is not an electrophilic addition. It's in the wrong chapter as far as I'm concerned. It makes sense if you're going to talk about alkene additions to put it there. But the alkene, when you do a hydrogenation, the alkene is not being a nucleophile, the hydrogen is not being an electrophile. So there, if we were to hydrogenate these alkenes, this order goes away and the less stable one reacts fastest. I'm not going to, I used to ask that, but it's such a complete, I don't want you guys memorizing exceptions, right? I want you learning the basics of what we're doing. And that's hard enough. I know there's enough on your plate already. But when you look, if you ever do end up looking at hydrogenation again, just remember that's not really an electrophilic addition. So every other one of the mechanisms, even the reactions where I told you you don't have to know the mechanism, if you look at the mechanism, it always starts with an arrow going from the alkene somewhere else, right? So the alkene's acting as a base, giving electrons away. In hydrogenation, it's a little different.
You can go first.
All right, so I was just going to say, so is that stronger than the presence of a functional group? Like say if you had 3 with the nitrogen, the positive nitrogen on it, versus 4.
No, yeah. A nitro will pretty much kill the alkene, being a base.
So the functional group is more
Yeah,
important.
I should probably come up here, just because somebody might see that that reaction just didn't gonna happen. All right, chlorine. If you needed to add a chloride, you can take Cl minus, and it will actually be a nucleophile on that alkene. That alkene is so electron poor, it's an electrophile itself. You might see that in Orgo 2, depending what Dr. Jones wants to do.
I was going to ask, I don't have the worksheet with me, but there was 4 different ones, and I know that you said
The one you turned in? Yeah.
that reaction's really, really slow. So would that one be the slowest, or there was one where there was like?
So on the worksheet, I separated. The worksheet was basically this.
Yeah.
There was a nitro, but it was separated from the alkene through a benzene.
Right.
That one might, being separated by a benzene might let it work, but it would still be the slowest.
Okay.
And then there was a benzene that had a methoxy group on it. That would definitely be the fastest.
And then there's, wait,
And then there was an alkene that had a benzene and 2 methyls and a benzene and 1 methyl. The benzene with 2 methyls was going to be the second fastest, and then the benzene with 2 methyls would be the third. Yeah.
What about alkynes?
It all works exactly the same way. So all the reactions where the alkyne is a nucleophile, if you put an electron donor on the alkyne, it reacts faster. Put an electron withdrawing group on it.
What's going to be faster, like an alkene or alkyne?
It's a really good question. It turns out it depends on what the electrophile is.
Okay.
So for some of them, actually for most of them, the alkyne is a little faster. But there's a few notable. If the reaction involves a pure cation, then it's slow. But if it's got, like if you're adding Br2 or mercury or something like that, the alkyne's a little faster. I won't ask you to compare an alkyne and an alkene.
Okay.
That requires, there's too much structural change. Like I said, on the, you may not always see it, okay? But when I write a question about, for an exam, the one on the assignment you turned in Monday, there were 2. The slowest and the second slowest would be pretty hard to figure out. Because 2 things change, right? You change the number of alkyl groups and you change the functional group. So what you guys want to look for in those comparisons, and if you're ever setting up an experiment, what you want to try to do is change just one thing, right? If you change 2 things, unless you absolutely know what one of them does, you're not going to be able to follow the changes. I mean, that's just, so it's easy to say this, that's just basic science. And like I said, in chemistry, one of the things I really love about chemistry is we control molecules, so we can change one thing at a time. In most sciences, it's really hard to change one thing at a time, right? Sort of any biology, if you think about that, right? If I, say I'm going to test I made some new drug, and I'm going to test it on you guys. You're all chemically different. So, like I can make you eat different diet. You're chemically different. You eat different diets. You sleep. I mean, there's just so many changes that 10 of you is not nearly enough. 10,000 of you would be probably not enough. But it's hard to. That's why it's so expensive to do that. Anyway, I digress. Other questions?
Related to this or just in general?
Anything you like, actually, yeah. You can ask this. I'm done. That's all the material you're going to see from me.
So what we were just talking about, the reason why when you have the extra bonds, so like,
On the worksheet?
yeah. So for what reason is it that, I knew that it was faster, but for what reason is it faster that?
The methoxy one?
Yeah, well, no, not the methoxy group. The one that has the extra bond next to the double bond.
So it was like this
Yeah.
and
then-
this. That.
Yes, exactly, yeah.
It's the same thing as this.
Oh, okay.
So really the phenyl is just a substituent. It's a pretty good substituent too, because now, right, it's actually got 6 pi electrons it can kick in there. The benzene is going to basically accelerate incoming nucleophiles and outgoing electrophiles. Right? Because it can either absorb electrons or it can push electrons out. And then depending, so again, the top one here has 3 substituents, the bottom one has 2. So the top one, we would say, colloquially, it's a more stable alkene, but it's also the more nucleophilic alkene. And again, these alkyl groups are weak donors, so the difference in rate is not that big. Okay, so if I took these 2 molecules and I added them to the same flask with HCl or HBr or Br2, they're both going to react. Like I can't really have one of them react and stop the other. Whereas if I have these two, like I could put those in the same flask, add HCl, and the bottom one's the only one that's going to react. Because the bottom one's got an electron donor. And again, it's the same, you just draw electrons. All right, you can push those electrons, you can push the lone pair electrons on O all the way out to that basic carbon. And on top, should probably stop writing NO2 there. Right, you can take the pi electrons in the alkene and pull them all the way to one of the O's on the NO2. All right, so NO2 is a very strong electron withdrawing group. The OCH3 is a very strong electron donating group.
So not to change the subject, but I think this was the third reaction we did, the one involving boron.
Mm-hmm.
So I was just confused on the terminology here. You say it's a syn addition. By that, do you just mean that the OH and the H are added on the same plane?
Yeah.
Yeah.
So we'll do that with one of these. There's evidently a key floating around that I screwed up. It's known to happen. All right, draw the product of that reaction.
Are those two, is the reagent and the solvent, are they always going to be in that? Is it always going to be those two for this reaction?
Yeah, I mean, the bottom reaction's in water. Water is a solvent. Like, and you're never going to have like naked hydroxide. So this is going to be Na+, and the solvent would be water. The top reaction, the BH3, is usually going to be an organic solvent. So I mean, it's really two distinct steps.
So yeah, so I guess what I'm saying though is you're always going to have a peroxide with the BH3.
Yeah.
Okay.
So the first step, product of the first step, is that. The H and the B are going to add syn. So the H and the B are going to be on the same side. Right, this is product of step one. And actually, there's nothing else we can do with that in Orgo 1. I don't think you do anything with that in Orgo 2. But there's some really cool chemistry you can do with organoboranes that you might just add the borane across the double bond, and then off you go. So the second step is just going to replace the boron with an oxygen, and it's going to do it with retention. Right, so the H and the OH end up syn, and I drew an answer on a key that I had. I do those keys pretty fast. Like I'm human, like you guys are. So this is like some crappy thing I got to do at work, and I'm thinking to myself, syn, and so I put the methyl in the OH syn, which means the H and the OH would be trans. My biggest thing here, so if you put the H and the OH anti on an exam, you probably lose a point out of 4, say. The important thing is that the OH goes on in an anti-Markov-Markov sense. So the OH goes on the less substituted carbon. Yeah.
So if you were to have a situation where there is no more substitute carbon, like say they were both tertiary, or whatnot, and it was also, you would also get a racemic product. Would you get 4 products then?
Yeah, maybe. So yeah, that's the other thing. This is definitely racemic. I don't mean to imply otherwise, but if you guys show me Sin addition and you get it's anti-Markovnikov and you don't say there's another enantiomer there, I'm fine. And yeah, the ratio, and I'm telling you this story like it's only the anti-Markovnikov product. The anti-Markovnikov product is the major, but depending on the steric, like here, the steric difference between these two carbons is extreme, right? We got a phenyl and a methyl on one carbon, we just have a methyl on the other one. So that's a big difference. But if there's not much of a difference, so say you did this reaction with that, you're gonna get a significant amount of OH on both of those carbons. All right. And the other thing that and then if it was this, I mean, addition to either carbon is the same, it's symmetric. The way we actually combat that, and you guys don't have to know this, but you may see it in Orgo 2. Let's see if I can draw it. This will be fun. Something like this. We have, it's 9 BBN, 9 bora, bicyclononane. Anyway, big honking piece of organic stuff bonded to the twice to the boron and 1 BH. And so this is, right, this is sterically huge relative to the H. And so it's a little more discriminating, right? If you're looking for a steric effect, carrying some big caboose behind here is going to accentuate that. And so, like I said, the basic reaction here, the reaction that's important is the BH bond. You can have whatever else off that one boron, right? So, and in fact, you only really need a third of an equivalent, right? Because you still have 2 BHs here. And so this borane could then add into another equivalent of alkene. You'd still have a BH that could add in. So you could add that in 3 times. And each one would be a little more sterically selected. Yeah.
Could you do an ozonolysis real quick?
I can do an ozonolysis.
That is one of the mechanisms we need to know, right?
What's that, ozone?
Yes.
No. I showed it. And it's really too bad. There's one step in there that keeps me from asking you guys to know it. That just weird stuff happens. The first step and the last step are pretty sane. Draw the product of this, and then we'll call it a day. And if you gotta go, obviously you gotta go.
Can I ask a really quick question while we're waiting?
Yeah.
So this is like this refers to the fourth reaction I think we did, where it's just H, hydronium and water.
Mhm.
Do you get both from Markovnikov?
No, you only get Markovnikov on that.
Only Markovnikov.
Yeah. And again, then, like that one, so the question about, right, if I do a hydroboration here, I'm likely to get the steric difference between a methyl and an ethyl is not much. So I probably get O on both carbons. If I do H3O plus, I get a secondary cation or a secondary cation. I would definitely get both of those. right? So Markovnikov's rule only really works out if the difference in cation stability is pretty extreme. Okay, so in your ozonolysis reaction, you're just going to slice through the alkenes, or the alkynes. This works with alkynes as well. With an alkyne, you get a carboxylic acid. With an alkene, you get just a carbonate. Again, nothing's going to happen to the benzene. So this will give us ketone from this bit, aldehyde here, with 2 carbons between it and another aldehyde. So 1, 2, 3, 4. 1, 2, 3, 4. And then finally, a benzene bonded to a carbonyl. That's going to be an aldehyde. So those would be the 3 products you get. All right, that's it. That's all the materials. So thanks for hanging in there. I know this was not your routine, normal semester, but you guys are here at the end. That is an achievement unto itself. Yesterday I realized I sort of gave the speech like, semester's over. So you do have exam 3 on Monday, and then we will do some stuff after Thanksgiving. There'll be Zoom classes, synchronous. I will have synchronous Zoom classes during those scheduled class meeting time. There's not going to be any new material. All right? You guys have seen what we're going to see. So definitely, if you haven't yet, I mean, this weekend, study for exam 3, right? That would be crazy not to do that. But as soon as that's over, maybe not as soon as that's over, like go home, sleep in your bed. Hopefully you don't have to quarantine from family. Say hi, eat some Thanksgiving. Take a breather. But don't wait too long to start the final project. That final project is long. And the idea is not that you bang that out the night before it's due. So it's due on December 6th. I promise you, if you wait till December 4th or 5th, especially the 5th, you are going to be in a world of hurt. Like, it's not so much that it's hard, it's just long. So I always recommend that you don't spend too much time on any given assignment at one sitting, right? It is hard to keep your brain engaged for hours and hours and hours, right? If you start that on the evening of the 5th, you have to sit there and plow through it until you're done. If you start it, Friday after Thanksgiving, because nothing's going on then, do a problem every day. Do 2 problems a day, right? Do 1 in the morning, do 1 in the evening. That way it's not, and that way also if you get stuck on it, there's a synthesis problem on there, and they're not small or easy. So if you get stuck, and you almost certainly will get stuck, you can look at it, you can write some stuff down, spend no more than an hour, if that long, working on it, and then walk away from it and let it sort of percolate around your brain. All right, have safe travels, happy Thanksgiving, and thanks for a great class. Stay.
I have a meeting at 1.
Okay.
I got to run, but I was thinking